I would like to welcome all attendees, including any members of the Statistics Division and Innovation Division who are able to join us today. The title of today's webinar is Approaches to Missing Data, the Good, the Bad, and the Unthinkable. Our speaker is Karen Grace Martin. Karen is the founder and president of the Analysis Factor, a company that provides statistical consulting services and ongoing professional development through workshops and webinars. As a statistical consultant, she has worked with clients from undergraduate honor students on their first research project to tenured Ivy League professors, as well as nonprofits and businesses. She holds master's degrees in both applied statistics and social psychology. Before founding the Analysis Factor, Karen worked as a statistical consultant at Cornell University for 7 years. She also taught statistics courses for economics, psychology, and sociology majors at the University of California, Santa Barbara, and Santa Barbara City College. She has co-written an introductory statistics textbook with Stephen Sweet, Data Analysis with SPSS. All phones and microphones other than the presenters have been muted, so if you have any questions or comments during the webinar, please use the questions interface in the GoToWebinar control panel. These will be answered by Karen at the right time. So at this time, I'm going to hand things over to you, Karen. Thank you for presenting with us today.
Thank you very much. Okay, let me show my screen, and let me, before we start, just do a quick sound check. Can everyone hear me okay? Just go ahead and type in a yes. Thank you. Excellent. All right. Thanks. Okay, so today I wanted to really give you an overview of different ways of dealing with missing data. Missing data, I assume everyone is familiar with the problems it causes in most statistical analyses. And the thing is, depending on the situation of your missing data, sometimes the solutions to solving these problems make it even worse. So they can cause even more bias, more imprecision in your analysis. So we're just going to do an overview of some of the important concepts and some of the approaches. Okay. Before we really talk about what to do about missing data, I just want to make this very picky but important point about what missing data is and what it isn't. So a lot of times in data sets, we may have places where, you know, we have empty cells and it seems like there ought to be a data point there, but we don't, and it really shouldn't be there. So for example, first two questions here, and you may not do survey research, but hopefully you're familiar with these kinds of variables and these kinds of studies where, you know, if you're asking customers questions about their satisfaction with the product they bought, and they say, I don't know, that is generally a pretty legitimate missing data. There is an actual satisfaction out there, and for whatever reason, that respondent is not telling you what it is. Now, maybe they really don't remember buying your product, but at some point they had some satisfaction and you couldn't measure it. The second one, who did you vote for in the last election? Okay, this one was pretty recent, but a lot of times, maybe you're asking about an election that happened, you know, 8 months ago, and if somebody says they don't know, it might honestly be because they didn't vote. You know, they don't remember if they voted for a particular candidate. And if it's a big election, they probably remember, but you know, there are a lot of local elections and maybe people don't remember if they even voted in the, you know, county judge election or whatnot. So there may not be a vote that you aren't measuring in your data set. It's a different situation, and you, before you do anything else in trying to solve the problem of missing data, you want to make sure there is actually a piece of information out there that you're missing. Okay, same idea. These last two tend to occur in often if you're doing a study on, say, some sort of long-term study. This happens a lot in medical studies, but it can be if you're measuring failure time on a piece of equipment or something. Sometimes we have loss to follow up because the piece of equipment, something happens to it. So for example, I just did an analysis with a client where she was looking at algae growth on these plates out in the ocean, and she was measuring this long term and under different conditions and whatnot. Well, she lost some of her plates due to a hurricane. So lost data after a certain point, so lost to follow up. You want to really think, so beyond that time when she lost her plates, is there data there? Is there actual algae growth on a plate that no longer exists? Okay, so those kinds of things you really want to think about before you're, quote unquote, solving the problem of missing data. Okay, or if you're measuring patients over time, somebody who leaves your study still has a blood pressure that maybe you can't measure. Somebody who dies no longer has a blood pressure. So really want to think about these kinds of things. Okay, so I'm just going to use this diagram. We'll see this a number of different times to look at the different approaches. But basically, here's the very simplest example we could have where we have two variables, a data set with two variables, V1 and V2. And we would have cases in rows. So for example, we have all our data is observed for variable 1, and variable 2 has some data observed, and then everything down here is missing. So I just want to give you this visual because I'll use it as a way to show how we're going to deal with that missing data in the different approaches. Now, as a general rule, there are 4 basic approaches to dealing with missing data. Listwise deletion, you may have also heard called complete case analysis, and we're going to go through these in a little bit more detail. The second is what's called imputation or single imputation, and essentially what you're doing is you take each missing data point and you are replacing the empty cell with an estimate. Now there are many ways to come up with that estimate, but ultimately that's what we're doing here. And then we're treating that estimate as if it were a real data point. May not be surprising, that's a bit controversial, but another approach related to that is what's called multiple imputation. And the basic idea of multiple imputation is same idea. It's based on this idea of replacing an empty cell with an estimate, but we do it multiple times. And each time we do it, we use a slightly different estimate. And the reason for doing this is each one of these estimates will vary slightly. So we're able to capture the measurement error in that estimate. So it's a way of solving the problem that single imputation has of quote unquote pretending that estimate is a real data point. We don't have to act as if we have certainty about that data point anymore. We can add in that uncertainty in that measurement error by using multiple estimates. And we'll talk in a little more detail about this. Full information maximum likelihood is a completely different approach. In maximum likelihood approaches, we are not imputing data at all. We are not coming up with estimates for the missing data. What we're doing is estimating the statistics in the model differently using a different technique called maximum likelihood, which allows us to keep any observed data in the model and work with it. Okay, so we'll talk in a little more detail on all of these, but you could see totally different approaches to dealing with missing data. Okay, now I just want to give you an overview again of we have these 4 basic approaches, and even within these approaches there are many flavors, many different ways of implementing them. So how do we even decide which one we're going to use? Well, a key component is what's called the missing data mechanism. Is anyone familiar with these ideas? The missing completely at random? Go ahead and give me a yes or a no. Okay. Lots of both yeses and nos. Okay, thank you, everyone. Okay, so the basic idea of missing data mechanism is it's not exactly why the datum is missing, but it's more about the process by which missingness will occur, okay? Now, the names of this missing completely at random, missing at random, they're unfortunate names, in my opinion. They're too similar to each other, which makes them confusing. But here's the basic idea. If a data point is missing completely at random, it is a complete, basically the idea is the missing data is a complete random subsample of the data set as a whole. Okay, so literally, you know, like the plates getting lost in a storm. Okay, it has nothing to do with the values of the data itself. It has nothing to do with how much algae was on the plate. It has nothing to do with some of the conditions, like how much sunlight was on the plate. That was one of her key things, was whether there was sunlight directly on the plate or not. So it has nothing to do with any of the variables in our data set, just a complete perfect random sample. Missing at random is similar. It's really, it's a conditional randomness, okay? So the idea is when it's missing at random, if we condition on one of the variables in the data set, then it's a perfectly random subset. So for example, if we use our plates again, perhaps we had 2 locations for the plates, those close to shore and those out in open ocean. If it turns out those that are out in the open ocean are more likely to be missing, but within that group, within the group of open ocean, once we condition on that, once we control for the fact that we're only looking at plates out in the ocean, now it's a complete random sample. That's missing at random. Does this make sense? Give me a yes or no. Yeah, it's a weird concept. I admit. Yes, they are definitely unfortunate titles. Yeah, exactly. Someone said they'd need to see an example of each on paper. I actually have written quite a bit about this on my website, and at the very end I'll give you a link to some of the things I've written in more detail. But basically the idea is as long as we can control for something in the data set, that's so the missingness, the likelihood that something is missing is related to something we have information about. It's not about the actual value that's missing. Okay, compare that to non-ignorable. So non-ignorable missing data, it's also sometimes called missing not at random. This is the case where the missingness, so how likely a datum is to be missing, is related to its value. So if the patients that are sickest drop out of a study, if the plates with the most algae on them tend to, maybe their anchor gets eroded more quickly, something like that. In cases where you often see it in studies, certainly where you're working with people, and people don't want to, the people with the most quote unquote undesirable responses are the ones who don't want to tell you. You know, the cocaine users are less likely to tell you they're using drugs than the people, the non-users, those kinds of things. Those are the worst. Salary is another great example. Often people with the highest salaries are the ones who don't want to tell you. So in cases like that where the missingness is related to the actual missing value, that's non-ignorable. Those are the worst situation because the only way to, first of all, tell if the data are non-ignorable is to have information about the missing data, which is pretty rare to have. The only time you can really tell is in situations where you're kind of doing meta experiments, right? Experiments about your research and what, for example, the reason we know people with the highest salaries are less likely to tell us is because some people have done lots of follow-up surveys and things like that. In the survey literature, researchers have really followed out and figured that out. But if you're doing a new experiment, it may not be absolutely clear. Sometimes it's obvious, but it's not always. So it can be tricky to tell which one you have. There are ways of getting at it, but not necessarily coming up with a firm idea. Okay, so it's kind of like doing archaeology. You want to gather evidence for which situation you have, but you're never really going to know for sure. Now, this matters a lot because some of our approaches work better under specific of these mechanisms. Okay, and we'll talk about that as we go through each one. The other thing to think about is the percentage and distribution of missing data. So first of all, literally just how many observations have missing data, you know, a literal percentage. But it also matters not just how many observations have missing data, but how distributed is that across different variables. And again, it depends on the kind of analysis you're doing. If you have a lot of control variables, this would be, you could have the missingness distributed over many more variables. If you have a pretty simple experiment with a treatment and a control group and an outcome, you may not have such a wide distribution because you just don't have very many variables. So this really depends on the kind of data you're analyzing and the kind of studies you're conducting. But the other part to think about this is not just missing data, but missing information. And again, it's a very subtle concept. But for example, you can have half of the observations of a variable missing, so you have no information about that. So let's say income, just because that's such a simple example. Let's say you do a survey and a lot of people won't give you their income. 50% of the people don't give you their income. You may not be missing all the information about people's income, though, if you have other variables in your data set that are related to income. If, for example, you can ask them questions like, do you rent or own your house? What is your monthly budget? What kind of car do you drive? You may be able to have a whole bunch of other variables that give you information about that missing data. And that can supply information even though the data points themselves are missing. So again, important concept to think about. Do you have information in your data set about the missing values through other variables? And it's also something to think about as you're designing a study. If you know people don't want to tell you their income or tell you about their drug habits, or you know some plates are likely to go missing due to weather, if you can plan for that through other variables, that can be very helpful. And then finally, what analysis you will be using. Certain analyses can handle the missing data better than others. One of the approaches I mentioned was maximum likelihood. Some analyses use maximum likelihood estimation. Analyses with more control variables are usually more susceptible to problems with missing data. So again, you want to think about this at the beginning as you're thinking about how you're going to approach your missing data. Okay. So the very first approach is listwise deletion, and as I mentioned, this is also called complete case analysis. This is the default in most statistical software for most statistical procedures. And it's very simple, okay? And that's really one of its advantages. It's nice and simple. And basically the idea is that really we only contain cases with full data. So any cases, any individuals or units that are missing data on any variables, we drop from the analysis. Okay, is everyone familiar with this, I assume? Okay, great. Lots of yeses. Okay, excellent. And the thing is, believe it or not, it's not always terrible. So first of all, it actually, its biggest disadvantage is, well, there are two things. Power. It can cause problems with power if you're losing a lot of cases. Okay, so this nice big sample size that you created suddenly can get very small. But the other issue is bias. Okay, so what can happen, depending on your missing data mechanism, is you can introduce bias into your results. Now, it actually works, however, just fine if the data are missing completely at random. If those missing data are a true random subset of the whole data set, you will not introduce bias. Okay, so that's one reason to stop and think about and see what you can figure out about that missing data mechanism. And again, you will lose power. Sometimes a loss of power is tolerable. If you're not losing a lot of cases, or if the cases you're missing are on a variable you don't really need to include in your analysis, it's a control variable that you could replace with another variable, something like that, sometimes it's not a big problem. This is another time when you want to think about percentage of missing data. If you have a very small percentage of missing data and the data are missing at random, so there is bias included, that's being introduced, but that percent missing data is very small, and I'm talking like 1% or something, very small, then the bias is not going to be big enough to cause any problems. Yes, there might be bias, but it might be small enough that you're still getting reasonable results. The worst situations, and I've seen some pretty bad data sets like this is where the missing data is distributed across a lot of variables. That's when listwise deletion really falls apart. So for example, if you have, a model with, say, 6 control variables, and each of those 6 control variables is missing 5% of data, none of which is very large. But if they're different cases, you suddenly can lose half your data set because of the distribution. Yeah, exactly. I've literally seen cases, for example, I worked with somebody, she had a data set of about 150, and when she did a complete case analysis, she had 5 observations left. So, sometimes listwise deletion just decimates your data set so much it's just not even an option. Okay, before we move on, there have been a couple questions, so I want to just pause. So if you have any questions, feel free to type them in, and I'm also just going to scroll back up and see if there are any. Okay. I think most of these I answered as I went along. Yes, Dion says, would another example of MAR be if some of the cases were male, others female, and conditioned upon the gender, it was random? That is, random missing value among males, given that we know the gender is male. Is this accurate? Yes, that's exactly it. Lynn mentioned a group of samples that are dropped and broken. That's actually a perfect example of missing completely at random. Yep. Leslie asks, how do you keep bias out of assumptions? Like no income stated, house is worth 200,000 and it turns out to be Warren Buffett. That's a good question. So outliers by themselves don't necessarily lead to bias. And one of the key things to think about in something like this, and when you're approaching missing data, is the goal is actually not to replace the data accurately or end up with an accurate data set. We're not worrying about the data being accurate. What we are interested in is having the model parameter estimates be accurate. That's where we want to make sure we have no bias and we have accurate standard errors. So we may absolutely end up with, when we deal with the missing data, we may never get a data set that actually, is remotely accurate, and that's fine. We want accurate results. Does that make sense, that difference? Okay, excellent. And it can be hard. It can be, it's counterintuitive to allow imputations, for example, that are just wrong. However, they will give you better means, better regression coefficients, and that's what's really important. More accurate p-values. That's really what's important ultimately. James asks a great question. Is there a ballpark allowance for percent missing? It depends on, of course, it depends, no. I have seen simulation studies that have found that both multiple imputation and maximum likelihood were able to give unbiased model parameter estimates and accurate standard errors with as much as 50% missing data. But something like that really requires, when you get that percentage that high, again, that's where this idea of missing information is important. You have to have other variables in your data set that are going to tell you something about those missing values. So that's really key. Okay, so let's talk about imputation. So like I said, this is really imputing a single observation to replace the missing data point. And then we just basically analyze the data. Now, 20 years ago, 15 years ago, this was pretty much the best we could do. And it did often lead to better results, better estimates. But it depends on the approach. And I'm going to show you one of the worst ways to impute data. But there are different approaches. So have you all heard, I assume you've all heard of mean substitution or mean imputation. That's one approach. So that idea is we basically take the mean of everybody else on that variable and we use that as our imputed value. But there are many others. There's regression imputation, where you literally treat the variable. So for example, we could use variable 2 here, treat that as the outcome in a regression model that's predicting the missing values. So we would use the predicted values from the relationship between variable 1 and variable 2 on the observed values, and then we would predict those missing values from our variable 1 and substitute those in. Okay. So you can do that with or without adding a stochastic error term, so adding in a little error on that. There are other approaches like hot deck and cold deck. These are basically, the idea of those is you find someone in the data set, often random. Hot deck is randomly and cold deck is systematically. You find another individual in the data set with similar responses on the observed variables, and then you substitute in their value on the unobserved. This is also related to things like approaches like last observation carried forward, where we're extrapolating beyond the data in a series. Those tend to happen in longitudinal data sets. All of these, some will give you better estimates than others, and I'll show you why in just a moment. But all of them suffer from the same problem. And that problem is that we are treating an estimate as if it's a real data point, which means that estimate has more uncertainty associated with it than we are accounting for in the analysis. This means all your p-values will be too small because your standard errors will be too small. So even if you can come up with really great estimates, which sometimes you can, using some of these more sophisticated imputation techniques, you're still going to be underestimating standard errors. Now, let me show you a very simple example of where mean imputation causes problems and where something like a regression imputation solves some of those. And let me just grab a little pen here and let me get a different color so I'm not competing here. We'll use green. Okay, so what we have here are the blue circles are basically the actual data points. Okay, so imagine they were the actual data points, and you can see in these cases where there's a red dot in the middle, those were observed. Okay, so we observed this data point. This one we did not. This one here, there should have been a data point at that value, but it's missing for whatever reason. So we have to estimate it. And this would be missing on our Y variable, which is income. So we have years of education on the x-axis, income on the y-axis. This is a made-up data set, so don't read too much into it. But this is a very typical, there's a positive relationship between years of education and income. So you can see, for example, this one is missing, right? So we've substituted in the mean. And you will notice the mean income, everywhere there's one missing, we end up with the mean income. Is everyone following what I'm doing here? So all of these are the imputed values, these right here. And here we imputed the mean. Okay, so what literally happens, we think we're helping ourselves by having an imputation because then we don't have that huge loss of power, but this is where the bias comes in. By putting them all at the same value, essentially, we end up with this red dotted regression line in the imputed data set. Had we had the full data, we would have had the blue regression line. So we're actually underestimating the relationship between income and education by imputing the mean. Now, something like a regression imputation would be imputing values right on the regression line. So again, it might preserve the relationship and it will preserve the regression coefficient, but you'll notice, unlike real data points, now we have data points that are all right on the regression line. So we're going to underestimate the standard error, or the amount of the residual error around that regression line. So that's the big problem. And that's where the stochastic regression adds in an error term to each one. So for example, it'll just randomly add a normally distributed error term. So maybe this one actually ends up down here, and this one actually ends up here, and that one there, and so on. So again, it's better, but we're still treating it as if it's really a data point. Laura asks, do the values you put in from the regression imputation depend on a regression model without using the missing data? Yes, they do. So you are assuming that the relationship of the observed cases, the complete cases, has the same relationship. Yep, and you are assuming linearity. You can do a regression imputation with logistic regression or with a Poisson regression. You can also, fit a polynomial, for example. So if there is a nonlinear relationship that you can account for, you can do that, and you should. Okay. So you can see mean imputation really anytime you're interested in, well, pretty much mean imputation is virtually never justified. At the very least, you should go one step further and use something like a hot deck approach or a regression approach, both of which in many studies have been shown to give you more accurate estimates. James says, can one consider the distance of missing points from the line, then compute average off the line plus or minus? Yeah, and that's what the stochastic regression is. Of course, you don't know how far the missing points are from the line, but we have to assume that the missing points have similar distances to the observed points. And basically the idea is you look at their distribution of the distances, and then you randomly sample distances plus or minus from that distribution. Okay. But again, if we only do this once, if we do a single imputation, even with a really good method, we're underestimating standard error because the software doesn't know that those are estimates. Okay, but again, imputation does have a few advantages, single imputation. It works, the data have to be at least missing at random, so it's not going to work at all if they're non-ignorable. It will generally work just as well as anything else, again, if you have a very small percentage of missing data. It tends to be helpful in situations where the missing data is spread across many variables. It will work better in that situation than, for example, listwise deletion will. You want to pick an imputation method that is based on other variables. You want to use as much information as you have in your data set to get the best estimates you can. It also tends to work when p-values are not involved. There certainly are statistical techniques that aren't about p-values. Now, you may not use them, but for example, if you're running a principal component analysis or a factor analysis, there are no p-values in those. So having standard errors that are too small isn't really an issue in things like that. So sometimes accurate standard errors are not the most important thing. And again, this is where it depends on which analysis you plan on doing. Okay, so multiple imputation. I first heard about this probably about 15 years ago at a conference, and it was right when I was struggling with a really ugly missing data issue with somebody who had just a small amount of data missing, but spread across so many variables that she was literally losing something like 75% of her data. I heard about multiple imputation, and way back then you had to use specialized software to implement it, but now it's available in all the mainstream statistical software. And essentially what you're doing is you're running that imputation. You come up with the best imputation model you can, and something that includes a stochastic component. So something that is randomly adding in an error term. So what that pretty much comes down to, and again, there are many specific algorithms for doing these imputations and the software give you choices on these, and we're not going to get into any details of these, but essentially they all come down to either a hot deck method or some version of stochastic regression where we are coming up with predicted values and then randomly adding on some error. And the thing is, if you do this multiple times, you will get slightly different estimates in each one of these data sets. So you are literally creating multiple data sets, each one with a different set of estimates for the missing data. You then run your analysis separately on each data set. And then once you've computed each of your models, you combine the estimates from the different models. And there are very specific ways of incorporating in the standard errors the uncertainty or the differences in the parameter estimates from the different models. Jed asked if Minitab performs any of these methods. I have not used Minitab in a while. I would think it does, though. I'd be very surprised if it doesn't. And the thing is, you really do need software that's going to combine or pool those results because it's not the kind of thing you can do by hand. Yes, Carl asked, you include correlations observed between different variables when you randomly impute missing values. Yes, you're going to use the relationships between the variables with missing data and the variables with observed data to come up with nice, accurate estimates. It's a really cool technique. The assumption is that data are at least missing at random. So missing at random, missing completely at random, both work just fine. I have here any percentages missing. As I said, the simulation studies have really shown you can have a remarkably high percent of missing data. It does not matter if the missingness is concentrated or spread across many variables. If it is spread across multiple variables, you do have to run your multiple imputation on all the missing variables simultaneously. And it can get tricky because you need to predict all these missing variables at the same time. So it definitely gets complicated, but it's possible. Here's the key thing. The last point is key. You need to be using other information in your data set to come up with good estimates of these missing values. And there are definitely data sets where you just don't have that available. So coming up with unbiased parameter estimates, and again, multiple imputation done well will give you unbiased parameter estimates and the exact same standard errors you would have gotten if you'd had full data. It's really remarkable. But it really depends on those imputations done well. And the details can get pretty complicated, but you have to have good data in your other variables. That said, I just want to throw a caveat in here. This is incredible. And for example, that client I told you about who was really stuck with 75% of her data missing, this saved her dissertation. Like, this is, multiple imputation can be a real lifesaver. It is not easy to do well. It's easy to do badly. It's not easy to do well. Steve asked to please define good data in other variables. Basically, strong relationships between the variables that have missing data and the observed data in other variables. So strong relationships. Yep, you're welcome. And depending, again, on how spread out the missingness is, depending on the distributions of the variables with missing data, of course, if everything is beautifully normally distributed, then it's pretty simple. But that never happens in real data, right? You end up with count variables, you end up with categorical variables, you end up with skewed variables, so the less perfect your data, and we're assuming it's not going to be perfect if you've got missing data, the more complicated it is. VJ asked what software I'm using for multiple imputation. Any of the mainstream software can do it. R, SAS, SPSS, Data. I didn't check Minitab, but I'd be shocked if it doesn't. But there are also standalone packages. Solus is a standalone package. I'm trying to think. There are others. I haven't used any of the standalones in a long time because it's just more complicated to do that. Yep, in R, there's a mice package. Ramesh mentions there's a package, mice in R, and HMISC. Yes, there's also one Amelia in R. Palmer asks, Reliasoft. I've never heard of Reliasoft, so I don't know about that one. So in any case, if you're going to go to the trouble of imputing, you might as well do multiple imputation. The hard part of multiple imputation is coming up with the good estimates. So why not do that one extra step that is not difficult to do and now gives you accurate p-values as well as accurate coefficients? Ramesh says HMISC is good as it does multiple repetition. Yeah, I have not used that one personally, but I know I have used mice in R. And again, there are lots of choices in the specific algorithms you're using, and it really depends on distributions and patterns of missing data. Okay, Robert asked about when you would use oversampling to study the behavior of missing data. This could be similar to your multiple imputation. Yeah, you definitely could oversample in a situation where you're expecting missing data to then understand the missingness and so on. So again, yes, if you're doing sort of a meta study to understand it, that would absolutely, and if you're doing the same kind of experiments over and over, or types of studies and always working with the same variables, and missing data tends to be an issue, it could definitely be worth the time and resources to do that. Okay. There is, okay, as I mentioned at the beginning, maximum likelihood approaches take a completely different approach. Okay, how many of you are familiar with maximum likelihood in general? Just give me a yes or a no for things like logistic regression or mixed models or structural equation modeling. Okay. Okay, at a high level. Okay, very big mix of yeses and nos. Okay. Basically, maximum likelihood at its root is an estimation technique. It's a different algorithm, and theoretically, in theoretical statistics, it's a different way of estimating parameters. Okay, so just like OLS, we use ordinary least squares estimation, usually in linear regression or ANOVA. Maximum likelihood is a different technique. It turns out that least squares estimation is a special case of maximum likelihood. So if you did have full data, you would get the exact same results under a maximum likelihood model and like a regression or an ANOVA model. Okay, but when you have missing data, least squares can only do listwise deletion. So you've got listwise deletion or you've got to impute somehow. Full information maximum likelihood is a different estimation technique altogether. And here's the basic idea. It's all based on the likelihood of specific parameter values given the data. It's basically, the basic idea is it says, look, the data we have are a fact. We've got it. Given these data, what are the most likely values of the parameters? Okay, and that's how it comes up with parameter estimates. So what it does is it does this two different ways. First, it looks at all the cases. It looks at the complete cases and figures out the likelihood values of the parameters given the data, given these data. And then it also separately computes the likelihood values of the parameters given complete cases. Okay, so it does it both ways, and then it combines them. Okay, this is again something you could never calculate by hand. It's very iterative process. It's very computer intensive. But essentially what it's doing is it's just working around the missing data. Again, it's pretty cool. Again, it will give you unbiased parameter estimates and accurate p-values, accurate standard errors. Again, as long as the data are missing at random or missing completely at random. It can do also a remarkably high percentage of missing data. And it doesn't matter so much about the concentration or spread of the missingness across the variables. Here's the rub. We tend to be limited to specific models that we're able to run via maximum likelihood. Up until, well, yeah, things like mixed models can use the maximum likelihood in certain patterns of missing data. However, so for example, if you're running an experiment and it's a randomized block design and you happen to have some missing data in some blocks, maximum likelihood in the mixed models, not GLM, but a true mixed model, will work, will take this approach. Otherwise, if you want to do just like an ANOVA or a regression, you can run it using maximum likelihood via structural equation modeling software. Okay, or structural equation modeling procedures within other software. So I know Stata and SAS both now have new SEM procedures. Are you familiar with SEM? It tends to be really popular in social sciences, psychology, but you can use it to run just any regression model or things like that. Holly asked for the SAS procedure. Can I remember? They're new. They just came out in the past 3 or 4 years with new structural equation model. I think it's as of SAS 9.3. I can't remember off the top of my head. It is not an option in most procedures. Okay. You can run a GLM, a general linear model. You can run a general linear model with this in the structural equation modeling software. Actually, Scott just asked about generalized linear models like logistic regression. Up until recently, I would say, no, you're out of luck. I do know M+ uses, can do generalized linear models using the full information maximum likelihood, and Stata just came out with a GSEM, generalized structural equation models. I've never tried it, but again, it just came out, I think, within the last year. Stata and M+ are the only ones I know of that can do that, though. Wayne asked, how are the two likelihood sets of parameters combined? I'm not sure I have a good answer for that. It's part of this whole algorithm. It's, again, not something you could do by hand or even come up with a formula for. But it's part of these are iterative processes, and it's part of those algorithms. Okay, and Wayne also asked, did I hear right? One of your clients has 75% of her data missing, but via imputation, you were able to do meaningful analyses. Not exactly. She actually was only missing about 5% of the data, but it was 5%. She had something like 10 or 12 variables in her model. So she had 5% missing on one variable, a different 5% missing on another variable, a different 5% missing on another variable. So once she put them all together in the model, via listwise deletion, she lost 75% of her cases. Because all you need is one variable missing to get dropped with listwise deletion. But each case had most of their data. It's not that most of the data were there, but it was a pattern of missingness that sort of was decimating her data set. I notice we're at 2 o'clock, so there's one more question and I want to, okay, great. Great question. And let me just also, I promised at the end, I have put together a whole bunch of resources on missing data if you want to learn more. This at my website. I also just wanted to mention these are on completely different topics, but we do have some free webinars coming up as well. So if you're interested in webinars on other statistical topics, we just put these together. And we put them, gave you a nice, easy URL to find them if you're interested. So James's question, great question. So out of all the methods you presented, which one is the most robust that you recommend for most situations? My recommendation is to use maximum likelihood if you can. It is less prone to having to come up with a good imputation model, but it's limited in what analyses you can run. So if you do have analyses you can't run via the maximum likelihood, then you want to go to maximum or multiple imputation. Yes, Emil makes a good point. If the missing data from different variables are never in the same row, one has to ask why and think about what that may be telling you about the analysis. Absolutely, the very first step in any time you're dealing with missing data is to do a very thorough missing data diagnosis. In fact, I have a workshop on missing data, and it's a pretty like 8 or 9 hour workshop, and we spend a good hour or two just talking about diagnosing your missing data and really investigating the patterns, because that alone gives you a lot of information. Yes, excellent point. Philip asked if these slides will be available after the webinar. I'm happy to make them available. Ashley, do you have a way to make them available to people?
Typically, we just offer the recording on our YouTube channel, but if you have a copy that you're willing to send out, Karen, that would be fine.
Okay. Yeah, I'm happy to do that. Dion asks, if the missing data are from one or more categorical variables, is it better to use multiple imputation or full information maximum likelihood? It really depends on where those are in the analysis. So for example, categorical variables generally work just fine if they're predictors in maximum likelihood, not so much if they're outcome variables. Okay, I think I've gotten everything.
Okay.
All right, well, thank you, everyone.
All right. Thank you, Karen. That was a great presentation.
Thanks.
So for our attendees right now, we ask that you complete the short survey that will be available within GoToWebinar. And I did see a question on ASQ RUs. You should expect an email within the next day with the RU information. A recording of the webinar will also be available within a few days on the division's YouTube channel. That's youtube.com/ASQStatsDivision. Please be sure to share this webinar and our other archived webinars with friends, coworkers, and colleagues. Also, we encourage you to check out the division's LinkedIn page as well, and our events calendar, which can be viewed at asq.org/statistics. There we have latest news on webinars, conferences, and some other topics. That's all the time we have today. Thank you everyone for joining us, and thanks again, Karen, for presenting with the Statistics Division. I hope everyone has a great afternoon.
Thank you, you too.